Though I wonder if giving myself finite actual sets is like giving myself a semantics. Hmm. Well, it's no use now. We agreed to the contract, right? What do I mean? We were the ones who agreed that a set containing as elements A was an existent object. Really, we're the ones who implicitly agreed that we could specify elements of sets. Yeah, though, to what extent do we need that? Well, we used it in our proof that A is not an element of A. Yeah, though, I don't really like that proof. Oh no, actually, I do like the proof. I don't like assenting to the conclusion. Why do I have to admit sets containing elements into my set theory? Why would I? Why am I admitting? Why am I putting things in my boxes? Is what I'm saying here. Why would I put anything into these beautiful boxes I have? Anything? I'm gonna get thing dust on them. Where did I agree to that, incidentally? The pairing axiom. This is like asking the conditions under which we could generate, construct subtract down into a set that contains as elements A. So we say C cap equals A cap E1 comma dot dot dot. And then we have the set containing as elements A cap intersect C cap equals A. So this is a system whereby we shed all the non-A elements. Okay, and then well, I don't know what we would want to do with this though. I mean, so we can systematically target a set that contains A, and we can systematically target a set that contains B. But if I already have the set containing A and the set containing B, why wouldn't I just say C is equal to that set? So I'm elaborating the conditions under which we could well, if we started with a set that contains A and then an arbitrary number of non-A elements, we can immediately intersect down into A. Okay, if I instead said oh, well, that would actually be... Well, that doesn't have to be the empty set, but... no, that wouldn't be the empty set, because this is still... yes, because the point is that this produces the set containing A. Okay. And this would be a kind of restriction we'd want to place. Well, so the idea would be if I... So I am thinking... I know that the set containing as elements A exists, okay? And this means, in a way, in this context, what we're saying is this means I have a filter. And then what we're saying is that the set C cap with A and E1 through EM is a set that I could filter. If I have... Well, so this divides up the sets in a way. I mean that there are sets that contain A and sets that don't contain A. Among the sets that contain A, we can obtain the set containing as elements A by making the set containing A intersection C, or set containing A intersection the set that contains A, the aforementioned set that contains A. So we have a way of constructing down into this. We have an operation we can perform on any given set that, well, this will either produce the empty set or it will produce the set containing as elements A. And now I say this. The set containing as elements A intersection C cap is... let me think here. Well, if nothing else, we could say tau of x is equal to the set containing as elements A intersection x. And in this case, we'd be saying the set containing as elements tau of x such that x equals C cap. And that's going to give us a reduction down to the set containing as elements A. And then... So again, I want to say... I'm trying to... It's like I'm trying to get around saying that... I'm trying to get around saying that this is a named set. I'm trying to say that this set containing as elements A could be the output of an operation instead of an explicit construction. So like if I say... I start by saying C is equal to the set containing as elements A. C cap is equal to the set containing as elements A. Alright, so this is how I start. Okay, and then I have orange, and then I have dot dot dot. Okay. Whereas here we're saying C, okay, we can have red. Okay, C is equal to the set containing its elements E1 where for all E in this relevant domain, not E is equal to A. Okay. And now this would be red. Okay. And the continuation would be C cap intersection the set containing its elements A is equal to the empty set. Okay, and then we could have C cap is equal to the set containing its elements A, comma, E1. Where, well, we just see A right there, but we might also say there exists an E such that E is equal to A. Okay, and then C cap intersection A, which is equal to tau of C cap, we might say, is equal to A. And now I want to say okay, but this doesn't pose any. This doesn't really let us go where we're trying to go, does it? Oh, hold on. What do I mean? Well, what this actually references, what we actually use. Yes. B is an element of the set containing its elements B. Alright, so we would have to do, let me see. proof continues however it does. And then here, oops, not a problem. That also needs to go. And this needs to be exists. That should be lazy evaluation, as it were. That should be lazy evaluation in the sense that I should only write this coloring in. I should only write error colorings in when I'm sort of solidifying a page. Maybe I could tag. I could note that I've skipped a line because I think it's an error, and then when I go back I can make a final decision about whether there's a way of salvaging the line. And then I'd have the tag that I examined something for a mistake, and I wouldn't have the tag that it was a mistake. What are we trying to accomplish with this? We're observing that if we apply this tau operation, where we're saying tau of x is equal to x intersection the set containing its elements x, then we have two cases. We have that we get the empty set, and that would be the case if C cap does not contain a copy of itself. And then we have the case where C cap does contain a copy of itself. Which is a way of saying there exists an E where E is any element. Yeah, though how is this any different from... Well, it's like saying we could put a warning sign on any proof where we perform... we could put a warning sign on any proof. Okay, we say for every set this construction works, we can make this construction. We can expose any set to this kind of filter. And what is that telling me? We can expose any set to this kind of filter. Well, and I think part of the idea was to try to capture this and say the set containing tau of x is equal to the set containing its elements x. I don't think that clarifies what point I'm making. I'm trying to make the point that we're saying We're saying whatever that means. I just, going for it. So tau of x, the set containing these elements tau of x is equal to the set containing these elements x. What we're trying to avoid is saying x is equal to the set containing its elements x. So instead we're saying that it's about wrapping this output in a set marker, or wrapping this output in set brackets. If I said for all x, tau of x is equal to x, let's put another term in there, another possible recourse. For all x, the set containing tau of x is equal to x. Rather, the set containing its elements tau of x is equal to the set containing its elements x, or the set containing its elements tau of x is equal to the empty set. Okay. Okay, and then we say for all x, right, so we'd want to rewrite this with our definition of tau of x, the set containing its elements tau of x. Well, so we're saying tau of c is equal to c cap intersection c cap, or tau of x is equal to x intersection the set containing its elements x. So for all x, x intersection the set containing its elements x is equal to the set containing its elements x, or the set containing its elements tau of x is equal to the empty set. Or is it the set containing the empty set? To ease our cognitive burden here, we could do or the set containing elements tau of x is equal to the set containing its elements the empty set. And now a point would be we don't have to commit until it becomes syntactically relevant for some later conclusion. Okay, now what is the idea? So these are the two outcomes of running this operation to try to obtain a set containing as elements x that is syntactically interrelated with x, that is related by intersection to x, whatever that means. I don't know that there's any syntax for handling this idea that we've applied this kind of operation. It's interesting. We can attach tags. We can attach tags to sets. Through a similar kind of operation, we define some operator that provably puts a tagged element into a set with a tag. And the idea is that we could start defining axioms or theorems in terms of tags, in terms of things that will be or will not be true whenever we have tags. And yet it would not be because of the tags that theorems would be true or false. No, but the theorems would always be true if the tags were present. We would make sure of it. It's like we are so good at obeying the rules that we get this extra layer of this buffer layer of rule obedience. Like, we're obeying rules over here as opposed to obeying rules, or I don't know, we're obeying rules up here as opposed to obeying rules on the frothy surface of rule obedience. We're always obeying rules on this flat surface up here, as it were, so we don't have to deviate our constructions to work around rules. This is a little bit like tagging. Okay, but how do I keep thinking there's going to be a way to carry this syntactically into our earlier proof. Like, for instance, and most specifically, the proof that we did for Theorem 105. A is not equal to the empty set. Well, that would be a point. I guess we gotta get like a bookmark or something. It's also not really good to open and close these pages, I am thinking, because it rubs the pages against each other. We should have a preference for minimizing the amount of times we have to read back through. much more pleasant this is when it looks nice. I mean, in the past I'd say, I just throw it on there. It should look like garbage. It should look like you just thrown confetti onto the page and then stapled it into the paper. Why though? That's just how serious I am. I don't care what it looks like. It turns out I do. What axiom is this? The axiom of foundation. Obvious nonsense. Axiom of regularity. Well, okay, so actually, if we make this the set containing these elements, the empty set, so A is equal to the set containing these elements, the empty set. Interesting. We're just going to do both of them, and we're not going to care which one's correct. That's the way to go, really. A is equal to the set containing these elements. The empty set is equal to... Well, it's, yeah, so we're only going to be we're going to wrap this in a tau operation. Wait, so we're saying tau of A is equal to the empty set. Okay. Rather, the set containing these elements, the empty set. Okay. Interesting. Then what? So when are we going to learn fourth? When are we gonna learn fourth? Not yet. There exists an x such that x is an element of the tau of A, and for all y, if y is an element of x. Okay, so if we're saying tau of A is equal to the empty set, This is the only statement. This is the only satisfying statement, right? That's not quite the point here. Now, actually, if we take this at straight at face value, there exists an X such that X is equal to the empty set. Now, do we want to admit the empty set into our ontology? Maybe we don't. Why would we? Well, this is if we can't have the axiom of regularity if we don't admit there exists an X such that X is equal to the empty set, because otherwise we would run into an issue here, I guess. And for all y is an element of the empty set, then y equals. Yeah, let's see. So what we could do here, we like a sort of meta use of the binary color. So we have syntax error into aqua green, syntax error pink into green blue 1, incidentally green blue 0, syntax pink into green blue 1 gives me that this was the mistake, and these are getting grouped together according to that criterion. And then syntax pink into, so we don't call it an error, we say, I'm going to, it's like we're not concerned with labeling what we've done as mistaken or not. We're concerned with making syntax updates. Now, we happen to be concerned with making syntax updates so that we have the correct syntax, but as opposed to the incorrect syntax, yes. There exists an x such that x is equal to the empty set, and for all y is an element of the empty set, then y is equal to the empty set. Well, but again, notably, this is a contradiction. Y is an element of the empty set, so this statement is always true. And then, if we take this as an axiom, this statement is also true, which means the entire statement is true. And that is, let me see here. Okay. So that was teal red. Yeah, but this all rests on a mistake, right? What do I mean? We're saying tau of A is equal to the set containing these elements of the empty set. But that would be what we'd get if... yeah, I'm having a hard time wrapping my head around that. I'm gonna take a quick break. May you intervene with a pedantic question? Sure. Feel free. Unless I accidentally just banned you. No, I didn't. Alright, yeah, pedantic question. Feel free, go for it. Does your book use there exists an X or for all X without specifying a bounding set? Yes. Which I feel like makes things conceptually more difficult. But maybe not. I've never tried it the other way, so. You consider that an error because I'm pulling X from well undefined then. Yeah, though we also we also don't do things like finite operations for the most part, and actually that's why I'm pausing on this one because so what we're trying to prove, we're trying to use the axiom of regularity, which is a way of encoding the statement that A is let me think. This is the axiom of regularity is a way of encoding the idea that A intersection the set containing as elements A is equal to the empty set. And actually, this statement that there exists an X such that X is an element of A, and for all Y, Y is an element of X, then not Y is an element of A. This is interderivable. I can take this expression and derive the more typical form of the axiom of foundation, or axiom of regularity. I'm not sure what the name is in other contexts. Now, anyway, this one, however, the proof requires you to stipulate the set containing as elements A. You have to stipulate this. What, how are we confused? Hold on, let me pull up. Is X a set or an element or both? So I think the idea in this book, though I'm a little bit hazy on this, I think the idea is that you retain the ability to say or, as in we don't have to commit either way so long as we keep our statements within various bounds. And since we don't have to commit either way, we don't need an axiom that says X is an element. We don't need well, yeah, again, I'm kind of fuzzy on this. It's this system in this book is purportedly agnostic with regards to whether there are individuals or not, which I find quite interesting. Here we go. In mathematics, the axiom of regularity, also known as the axiom of foundation. So this statement, for all X, if X is not equal to the empty set, then there exists a Y where such that Y is an element of X. Hold on. It's a little bit different in the book. But there exists a Y such that Y is an element of X, and Y intersection X is equal to the empty set. This is interderivable with this statement, this restatement of the axiom. However, the proof requires us to stipulate that there's a set containing as elements A, as in we would have to stipulate that there's a set that contains elements, which I don't want to do, so I'm trying to work around it. Let me see. Yes, that's true. But I'm saying what I don't like to allow in. I think I see the point you're making. And I'm trying to move forward as if this is treating this purely as syntax. Like claims that, like if I want subset status, I can say if X is an element of A, then X is an element of B, but I don't want to stipulate particular finite sets like this. I don't want to use curly braces unless I'm doing abstraction. I don't want to use curly braces to specify particulars. Here, this doesn't specify particulars. It specifies that there's some element that such that that element is an element of another set. Does this say no set can contain a set that contains the set itself? Yeah, that's roughly the idea. Or it may be exactly the idea. Does this say no set can contain a set? Well, it's a way of getting what the author immediately wants to prove using it is that A is not an element of A. For all A is not an element of A. That's not exactly what the theorem states. Actually, it took me quite a few pages to figure out what the theorem is actually saying, mechanically speaking, in this rendering of it. Avoid Russell's paradox, yes. Which we do using this axiom, purportedly. Now, one of the points I made was that, let me think here. I'm exploring this idea of wrapping A in an operator. So this is all exploring the tau operator, a tau operator here. And the idea is that if I apply this tau operator in advance, so this tau operator says tau of x is equal to this is equal to x intersection the set containing its elements x. Okay, so if we have a case where that is producing the empty set, I think I made a syntax error here incidentally, but we get one of these as the output. So we're saying for all x, for any given set, you can do that. So tau is a general, like you can define any kind of operation you want to perform with it. Now, I don't know if there could be something that restricts me from doing this that I've unwittingly agreed to. Tau of x is always empty, you claim. Well, so first I'm exploring the observation that the axiom of regularity is satisfied if the set containing as elements tau of x is equal to the set containing the empty set. So this, working through this syntax gives me that, so we're saying x is an element of tau of A. Let me see here. So we're replacing A. We're wrapping A in this operator, and now we're saying x is an element of tau of A. Now, if the set containing tau of x is equal to the set containing the empty set, then x is an element of tau of A becomes the statement that x is equal to the empty set. And then, let's see. And then we have y, which is an element of x, becomes y is an element of the empty set, which is false, making the consequent true. And then we have the only remaining statement in this and is there exists an x such that x is equal to the empty set, which we agreed to earlier. Though we could also strip out that axiom, and then this statement depends on whether we admit the empty set or not. But the empty set is involved in so many proofs, we have to allow it effectively. Let's see. So because they're unary sets, let me think here. Well, if you're talking about this, let's ignore the top one. This one, the set containing its elements tau of x. Let's see. The set containing its elements x is equal to the set containing its elements y. Yes, so we would be admitting that. Though, yeah, that's true. Then how does that sidestep admitting a set like this into our theory? Because so this is like a roundabout way. This is a way of avoiding saying that we have a set containing a unit or an individual. It's whatever we happen to get out of this tau operator. You don't need elements. Yeah, that's what we're going for anyway. Could be sets all the way down, or we could have elements, but I think of that as a kind of concession. So if I don't have to make that concession, I would prefer not to. Now, I mean, the resulting set theory might be useless, but I don't care about that. Think we can create elements from sets themselves. All numbers are technically sets. Well, in the sense that you can play the games that you play with numbers by using sets. And when people perform analysis, sometimes they start analysis by constructing numbers out of sets. Saying numbers are sets without that kind of context, it doesn't... Well, so, but then the follow-up point is you can construct sets that let you play those games. Play the number games. I think we can create elements from sets themselves. Conveniently, we haven't needed elements up to this point. This is like a pure set theory that only cares about membership predicates, as it were. But nice. If it's working, I think it might be working. But yeah, the author tries to get us to agree early on to, let me see, the axiom of pairing. Let's see. And that says, here we go. So the axiom of pairing... And when you say for all x, you mean x is any given set, yes. Now, whether we've succeeded in maintaining that kind of purity, I don't know. But, so here we have the pairing axiom, which says for all a, or no, there exists an A such that for all z, z is an element of A if and only if z equals x or z equals y, which proves syntactically critical in making statements like the set containing its elements x is equal to the set containing its elements xx. As in, this is where we get the right, by the author's reckoning, where we get the right to put an element in a set. And I don't think we require this. But again, I might be wrong. At any rate, this here is an effort to avoid having to invoke such a construction. Fascinating. Yeah, this book has been... At first, I really didn't like this book, but it's really grown on me. This activity makes you think. I mean, I didn't even realize I was maintaining this kind of division, but then we got to this point and I was resistant. Like, no, I don't want to, because yeah, the proof that the author uses, actually I can, so I've marked here B is an element of B, B is an element of the set containing its elements B. Invoking this construction repeatedly and sort of cycling it through the syntax was required for the author's proof, which set off alarm bells. Like, if I want to follow through on the syntax of the author's proof, I have to keep reintroducing this false... Well, so this is a proof by contradiction, so I have to reintroduce this false statement over and over again, so that when I feed it through the syntax, the syntax ends up delivering the end of the proof. seems suspicious to me. Yeah, like here we feed in the syntax, we feed in the contradiction again. It's like this proof was a kind of reductive process where you repeatedly feed in a contradiction to activate the syntax in a required way. Which is interesting. However, it's also highly suspicious. Because I mean, when I work through, e.g., geometry proofs, like if I work through a proof in Euclid, Euclid doesn't have to do things like repeatedly introduce a contradiction to make a square fall out. So why does it have to happen in this case? Kind of a strange question. It seems like you're doing induction. Interesting. It's like some kind of hidden connection here. It's like there's a stored up, some stored up quantity that we're churning through by repeatedly applying this contradiction. It's a funny idea. Well, and that is more how we're, yes, and because it's finite, you will always finish. Interesting. And this is more how we're thinking about the set theory we're constructing. The amount of semantics I'm doing, I'm trying to do every proof purely syntactic, with no appeal to contradictory examples. So we don't construct sets. I mean, sometimes I'll go through and talk about what the set would have to be describing, or what the theory, like I'll, let's see, assume I'm familiar with lean and have chosen not to do it, not to use it. Funny you should mention that. I started studying lean a few days ago with a language model. I'm not far into it, but the project that I've started is that I'm going to write, or I'm going to identify a highly syntactic, yeah. I'm going to identify a subset. So I only know Racket, the programming language at the moment. I'm going to identify a subset of Racket that is transliterable to lean and vice versa. So I could write programs in Racket and have them and port them over to lean so I can run proofs on them as a way of introducing myself to lean and its proof system. We're going to use it to prove various characteristics of leak code solutions that we write. I tried working through the set theory puzzle game with lean that you can find without too much searching, and I couldn't get into it. But now I have a more developed appreciation for this kind of belabored formalism. It's a bit tedious, yeah. Well, this is a bit tedious too, and yet I feel like I'm learning a lot. It's, I think it'll be nice to have certainty. Am I going to write the grammar for math? Not yet. Hmm. I also just like the output of this activity. So I like my notebooks. Nice keepsakes. Anyway, yeah. So I'm wondering, I'm doing this in calculus. I want to read a constructive analysis textbook. But I'm thinking, it keeps striking me I should drop the calculus and just do this, because I could do this for hours. I, I could sit down and do this for 3 hours straight and not think about it. I don't know why I don't know why I'm so able to do this. We're almost into relations and functions. Watch and comment for, well, let's find out. Alright. Well, I only have about 15 more minutes today, but I'll be doing this again tomorrow. Let's see. So immediately after saying I could do this for hours and hours. Yeah, however, I'm going to end it shortly. Yeah, so we're working back through Theorem 105 because it's going to prove relevant for the next theorem we have to work through. Could doesn't mean I will. Yes, I keep a pretty rigid stop time for the day. I'm not so tired that I'd have to give it up, but alright, let's see. So we've got for all x intersection the set containing its elements x is equal to set containing its elements x. Okay, I think I see the point here, which is that this component, let's mark it with the trinary, the zeroth color here. This statement, so I didn't know which of these two I should choose as the best rendering here, but I guess it should be, yeah, I think we'll mark this as error. This expression, x intersection the set containing its elements x is equal to the set containing its elements x, is the OR of this. So we have these two expressions. Yeah, so this is like a, I want to say this is not an assertion that we'd get directly from axioms or definitions. This is an assertion we get out of an observation about how sets work. So this OR expression is set up. Well, I might observe this OR expression we get from semantics, or what I'm here identifying as semantics, I guess. What do we mean? So we're saying up here we say C cap is equal to the set containing its elements C cap. Alright, and that's what the author grants. Okay, then an alternative to this is that C cap is equal to a set that contains arbitrarily many elements that are not equal to C cap. Okay, then C cap intersection the set containing its elements C cap is equal to the empty set. And then the final case, the only other possibility, so it seems, is that C cap is equal to the set containing its elements C cap and then an arbitrary number of elements that are not equal to C cap. Then there exists some E such that E is equal to C cap. Okay, and now we say C cap intersection the set containing element C cap is equal to C cap. Alright. Now though, this only gives us a kind of wrapper, a kind of removal from claiming that there's a set that contains an individual. I don't know how comforting that wrapper is. But okay, so we're saying... Well, so this is also incidentally saying tau of x is equal to the set containing its elements x. Rather, the set containing its elements tau of x is equal to the set containing its elements x. Am I doing this right? We have to wrap that in sets as well. Yeah, well, one wonders why we're giving ourselves arbitrary ability to wrap expressions. Well, I think that would come down to, I think what we would need to show maybe is that we have the ability to step up a tau expression. Let's see, so if x is equal to the set containing its elements 1, 2, 3, then the set containing its elements x is equal to the set containing its elements 1, 2, 3. Makes sense to me. And that is effectively how we are using it, yes. Though then, why would we grant ourselves that ability? Well, it doesn't make us commit to individuals, at least. I guess maybe I'm wondering, could we do entirely without curly braces? Without assertions that we know what the contents are of sets? So we're claiming tau is always empty. Well, no, so the point is that... the point here is that the axiom of regularity is a tautology. No, hold on. I think what I'm saying is that, and maybe I should rewrite rather than lingering here, I think what I'm saying is that the axiom of regularity is a tautology if tau of x is equal to the set containing its elements, the empty set. And then the idea is that the only other possibility is that tau of x is equal to the set containing the set containing its elements tau of x is equal to the set containing its elements x. These are the only two possibilities for tau of x because of how we constructed tau of x. Though, am I making sense of that? Let me see. Yes, that makes sense to me. It's either the set containing, so the set containing its elements tau of x is either equal to the set containing its elements x, or it's equal to the set containing its elements the empty set. In the case where the set containing its elements tau of x is equal to the set containing the empty set, the axiom of regularity is a tautology because it turns into saying that there exists an x such that x is equal to the empty set. And then in the case where we're saying our wrapped a, tau of a, though even it's like we'd want to say row of tau of a because we still have to wrap this in sets, but okay, our prepared set, if this is the equality that maintains for our prepared set, when we pass this prepared set through the axiom of regularity, we can prove that A is not an element of A. But what does that actually tell me? Because mainly what this is doing is back here whenever we had to say B is equal to the set containing its elements B, this kind of thing. Instead of saying B is equal to the set containing its elements B, we're saying tau of B is equal to the set containing its elements B. And what I'm proposing is that this wrapping of A in tau is giving us the ability to use expressions like these for our proof without committing to saying something like B is equal to the set containing its elements B. We don't have to construct a construction like this, or rather our replacement for this kind of construction is saying the set containing its elements tau of x is equal to the set containing its elements x. And now we have a kind of yeah, so the interest we might have for this proof depends on how interesting we think it is that, or how interested we are in this set containing its elements tau of x. I mean, this being our replacement for A in the proof that A is not an element of A. Instead of saying A is not an element of A, we'd say I'm not sure. I'm losing it. So you already have the axiom that if S is a set, then the set containing its elements S is also a set. Huh. That's a good question. Maybe I'm overreaching. Do I have that axiom? Actually, I have... it's the singleton axiom. I might have to rewrite this. Actually, hold on, I tried working through this book months ago, and I ended up despising it. And then I came back, and now I'm fine with it. But during my adventure, I made this. Okay, let's see. Let's see, what is that? Is that on screen? Yeah, let's see. Doesn't look like we claim that. Maybe we have definitions. Yeah, even in this collection, the only way we end up getting curly braces around sets is through this. There aren't any curly braces prior to this claim that there's some set containing its elements x and y. Let's see here. Might be derivable from the power set axiom. So axiom pair, yeah, the pairing axiom. Let's see. Well, yeah, so the author wants us to take that definition from the pairing axiom. give ourselves the pairing axiom, and then we rewrite it in the form of a definition. Other than that, though, the definition schema of abstraction. Yeah, though, saying, I don't know if we could get, I don't know if we can arbitrarily wrap sets or wrap elements in sets as a result of saying, like, if I said that, if I had an operator that I said applied set wrappers, I could say phi of x is the operator that applies the set wrapper, and then this is the set containing its elements, those elements to which I have applied the set operator, or something like that. The set wrapper operator. I don't know. This is all getting a little bit confusing. Axiom pair used on S and S. Yeah, so then in that case you could look at the definition as, yes, well, I mean, the point of this definition is to go in the other direction. Though, I mean, you can go in either direction. You can make some proofs happen by having access to the set containing its elements x and x. Yeah, we can also go in the other direction to acquire a singleton. So we have, right, our set containing its elements x, y, except that instead of x, y, it's x, x, and that reduces to x. Set wrapper could just be annotation. Well, I'm originally what I was setting out to do is see if, well, maybe this is gesturing towards a more general principle, which is that this is characterizing what we get when we wrap a set in set braces. The kind of general behavior. Yeah, and the way I'm thinking of this practice, I'm thinking about it as a practice, as by which I mean, think here. Well, I mean, even down to the coloring scheme. This is a practice where we impose rules on what we say, what we're willing to write down, and then we follow the rules. So I'm more interested in, I guess I'm interested in finding regularities in my own syntax usage. And figuring out what I have to mean given the way I use syntax. Anyway, I am going to call it as it is end of day. I will be back in roughly 11 hours. I'll be back in 10.5 hours for coding. Yes, actually, I'll be studying Lean in about 10.5 hours. Incidentally. Do that for about 3 hours and then do some leak code. Not sure if you can be there, but cool. Yeah, I'm gonna pick it up. It's partially an exercise in just learning another programming language. Gives me a kind of project to work towards while I'm learning to engineer software. Well, while I'm learning data structures and algorithms anyway. Anyway, have a good day. If you are back again, I will see you next time.